Good evening, and welcome to The Quiet Explainer. Tonight, we explore how global shipping connects the world. Not loudly, not dramatically. Just follow the journey at your own pace. If you find value in calm explanations like this, you can subscribe for more. Only if it feels right. For now, imagine the planet at night. Most cities asleep, while far out at sea, thousands of ships move steadily through the dark. And that is where we begin. Look at the Earth from far away, a dark sphere turning slowly in space. City lights glow softly along the coastlines. Most homes are quiet. Most people are asleep. But the oceans are not empty. They are not still. Across the surface of the sea, thousands of ships are moving. They move steadily. They move predictably. They move almost all the time. Global shipping does not sleep. It does not rush. It does not pause for headlines. It continues. Every hour, every day, every season. These ships carry containers, fuel, food, raw materials, machines, clothes, electronics. Many of the objects around you once crossed an ocean. They traveled quietly. Before they reached a store, before they reached your door. The ocean covers more than 70% of the Earth's surface. Water connects the continents. Land divides them, but water links them. Shipping uses this natural network is less than #0. 5# is greater than ships. Follow established sea lanes. These routes are shaped by geography, by currents, by wind patterns, by trade demand. At any given moment, satellite systems track vessels across the globe. Each ship broadcasts its position, its speed, its direction. The movement looks slow on a map, but it is constant. This constant motion forms a pattern, a steady circulation. You can think of global shipping as infrastructure, not visible from most cities, not often discussed, but foundational. Without it, modern trade would shrink dramatically. Many countries depend on imports. Many depend on exports. Few nations produce everything they consume. Consider food. Grains move between continents. Coffee travels from equatorial regions to colder climates. Seafood crosses oceans in refrigerated containers. Energy moves by sea as well. Oil tankers cross major routes. Liquefied natural gas carriers link producers and consumers. Raw materials travel too. Iron ore, coal, bauxite, timber. These materials feed factories. Factories produce goods. Goods return to ships. This cycle repeats quietly, continuously. On land, we see trucks. We see trains. We see warehouses. At sea, movement feels distant. The horizon hides activity. Yet maritime transport carries the majority of global trade by volume is less than hash 0. 5 hash is greater than mass. It is efficient for heavy cargo. It is cost-effective over long distances. Ships move large quantities in a single journey, far more than aircraft can carry. Air freight is faster, but it is expensive and limited in capacity. Shipping moves slowly, but it moves at scale. Scale is the key idea. A single large container ship can carry tens of thousands of standardized containers. Each container may hold thousands of products. The math becomes clear. Small shipping cost per item. Large total movement. This system depends on coordination. Ports schedule arrivals. Pilots guide ships into harbors. Tugboats assist in tight spaces. Cranes lift containers with precision. Trucks and trains wait nearby. The timing matters. Delays ripple outward. Congestion in one port can affect supply chains across continents. But most days, the system works steadily. Not perfectly, but reliably. Ships are engineered for endurance. Steel hulls, large engines, advanced navigation systems. Crews rotate through long voyages. They maintain equipment. They monitor weather. Weather shapes routes. Storms can delay arrival. Currents influence fuel use. Yet over time, averages stabilize. Routes become predictable. Predictability supports planning. Planning supports global commerce. Imagine a store shelf. Rows of products is less than hash 0. 5 hash is greater than different brands. Different origins. Many traveled by sea, often more than once. A product may cross an ocean as raw material, cross again as a component, cross again as a finished good. This layered movement is normal. It reflects specialization. Countries focus on what they produce efficiently. Trade fills the gaps. The oceans make this possible. Wide, open, connected. Shipping lanes are not random. They cluster along efficient paths. They pass through narrow points between land masses. These narrow points are strategic. They shorten journeys. Over decades, global trade patterns have shaped these flows. Manufacturing centers linked to consumer markets. Resource-rich regions linked to industrial regions. The system is physical. Steel ships. Concrete ports. Fuel. But it is also informational. Schedules. Contracts. Digital tracking. Modern ships rely on satellite navigation, automated identification systems, electronic charts. Ports use logistics software. Companies monitor cargo in real time. Information reduces uncertainty. Reduced uncertainty lowers cost. Lower cost supports trade. There is a rhythm to all of this. Departure, transit, arrival, transfer, then departure again. This rhythm continues through holidays, through seasons, through political cycles, is less than has hone. 5 hash is greater than. It is not dramatic. It is procedural. A system built over decades. When we say global shipping connects the world, we mean something concrete. Goods move between distant regions. Economies become interdependent. Consumption and production separate geographically. The connection is not symbolic. It is logistical. And tonight, while lights dim in many cities, engines continue to turn far from shore. Radar screens glow on quiet bridges. Crews maintain watch. Across the Pacific, across the Atlantic, across the Indian Ocean, movement continues. This steady circulation forms the backdrop of modern life. It supports supply chains. It stabilizes markets. It enables specialization. And most of the time, it does so without attention. In the next section, we will step back in time to see how ocean trade began and how it evolved into the system we rely on today. Now we move into a brief history of ocean trade. For thousands of years, people have looked at the sea and seen a pathway, not a barrier, a pathway. Long before engines, long before steel hulls, there were wooden vessels, small at first, then larger. Early coastal communities traded with nearby settlements. They exchanged food, tools, textiles. These journeys were short, often within sight of land. Over time, confidence grew. Navigation improved is less than #0. 5 hash is greater than boats ventured farther from shore. In the Mediterranean, ancient civilizations built structured maritime trade networks. The Phoenicians were known for long-distance seafaring. They established ports across the Mediterranean basin. They traded metals, timber, glass. The sea became a commercial highway. In parallel, the Indian Ocean supported seasonal trade. Merchants learned to use monsoon winds. They sailed with predictable wind cycles, then returned when winds shifted. Predictability mattered. Wind patterns created structure. Trade linked East Africa, the Arabian Peninsula, India, Southeast Asia. Spices moved west. Textiles moved east. Ideas moved in all directions. Maritime trade was never only about goods. It also moved culture, language, technology, Ships were powered by sail. Their speed depended on wind. Their routes depended on currents. Navigation relied on stars, on coastal landmarks, on accumulated experience. Knowledge passed from one generation of sailors to the next. Gradually, trade networks expanded beyond regional seas. By the medieval period, maritime trade connected large parts of Eurasia. Chinese merchants operated large junks in the South China Sea. Arab traders crossed the Indian Ocean. European merchants sailed the Mediterranean and parts of the Atlantic. These systems were complex, but fragmented is less than #0. 5 is greater than. Different regions controlled different segments. Then came a period often called the Age of Exploration. Beginning in the late 15th century, European powers sought new sea routes. They aimed to reach Asian markets directly. Maritime exploration intensified. Voyages rounded the southern tip of Africa, crossed the Atlantic Ocean, linked previously separate trade systems. Oceanic navigation improved with better maps, more accurate compasses, advances in ship design. The result was a gradual integration of global trade routes. Silver from the Americas traveled to Europe and Asia. Spices moved from Southeast Asia to Europe. Sugar and tobacco crossed the Atlantic. Maritime trade became intercontinental. It also became tied to empire. Naval power protected trade routes. Merchant fleets expanded under state support. Over the centuries, ships grew larger. Hull designs improved. Cargo capacity increased. Yet sails still depended on wind. Travel times remained uncertain. The next major shift came with steam power. In the 19th century, steam engines were adapted for maritime use. Ships no longer relied entirely on wind. They could follow more direct routes, maintain more consistent schedules. Coal-powered steamships reduced travel time across oceans. Reliability increased. The opening of major canals further reshaped trade. The Suez Canal created a direct link between the Mediterranean and the Red Sea is less than #0. 5 is greater than. This shortened the route between Europe and Asia. Later, the Panama Canal connected the Atlantic and Pacific Oceans, reducing the need to sail around South America. Geography was reshaped by engineering. Steam eventually gave way to diesel engines. Fuel efficiency improved. Range increased. Steel replaced wood as the primary material for hull construction. Ships became stronger, larger, more durable. Global trade volumes expanded during the Industrial Revolution. Factories required steady supplies of raw materials. Finished goods sought distant markets. Maritime transport supported this expansion. By the early 20th century, global shipping was already central to the world economy. Major ports handled coal, grain, manufactured goods. Two world wars disrupted maritime trade. Naval blockades limited access. Merchant fleets were targeted. Yet, after each conflict, shipping networks were rebuilt. Trade resumed, then expanded further. In the mid-20th century, another transformation began. One focused not on propulsion, but on cargo handling. Before this change, goods were loaded piece by piece. Crates, barrels, sacks. This process was slow, labor-intensive, prone to damage and theft. Ports were crowded with dock workers. Ships remained in harbor for days or weeks. The inefficiency limited growth. The solution emerged gradually is less than #0. 5# is greater than standardized containers. Instead of loading thousands of individual items, cargo would be packed into uniform metal boxes. These boxes could be transferred easily between ship, truck, and train. The concept reduced handling time, reduced cost, reduced uncertainty. Containerization began spreading widely in the second half of the 20th century. Ports adapted with large cranes. Ships were redesigned to stack containers securely. This change accelerated globalization. Manufacturing could move to regions with lower labor costs. Goods could reach global markets efficiently. Trade volumes increased sharply in the late 20th century. Supply chains stretched across continents. Maritime shipping became more standardized, more integrated, more data-driven. Today's system rests on these historical layers. Ancient roots, age of exploration linkages, steam power, reliability, industrial-scale production, container standardization. Each phase built upon the previous one. None replaced the ocean as the core medium. The sea has always been central, wide, connected. What changed was organization. Ships evolved. Navigation evolved. Institutions evolved. Through centuries, the purpose remained steady. Move goods between places separated by water. Slowly at first, then more efficiently, then at global scale. This long history explains why modern shipping feels both advanced and familiar is less than #0. 5# is greater than advanced in technology, familiar in purpose. People still rely on the sea, as they did thousands of years ago. Only now, the network spans the entire planet. From early coastal trade to container megaships, the pattern is clear. Expansion, integration, standardization. And this sets the stage for the next transformation we will examine. Now we move into the container revolution. Before the mid-20th century, Cargo moved piece by piece. Boxes were lifted individually. Barrels were rolled by hand. Crates were stacked carefully in ship holds. This method is called break bulk shipping. It required large crews. It required time. It required constant supervision. A single ship could remain in port for many days, sometimes weeks. Loading was slow. Unloading was slow. Each transfer increased the chance of damage. Each transfer increased cost. As global trade expanded after the Second World War, these limits became more visible. Manufacturers wanted reliability. Retailers wanted predictability. The shipping industry needed a simpler system. The solution was standardization. Instead of handling thousands of small units, cargo could be packed into large metal boxes. Each box would have uniform dimensions. Each box could be moved as a single unit. One of the key figures behind this shift was Malcolm McLean. He was an American trucking entrepreneur. Is less than -0. 5 is greater than he understood. Inefficiency in cargo handling. In 1956, a converted tanker ship carried standardized containers between ports in the United States. The experiment demonstrated something simple. Containers reduced handling time dramatically. Instead of loading individual packages, cranes could lift entire containers, from truck chassis onto ships and back again. The concept seems obvious now, but at the time, it required coordination. Ports needed new cranes. Ships needed redesigned decks. Rail systems needed compatible flat cars. Standard sizes became essential. Over time, international standards defined container dimensions. The most common length became 20 feet, often called a TEU, or 20-foot equivalent unit. 40-foot containers also became common, known as FEUs. These standardized boxes could be stacked securely, locked together with twist lock mechanisms. Ships were redesigned to carry them in vertical stacks, both below deck and above deck. Ports invested in gantry cranes, large steel structures that move on rails. They lift containers with precision. A single crane can move dozens of containers per hour. Time in port decreased sharply. What once took days could now take hours. Cost per unit fell. Theft decreased. Damage decreased. The container also enabled intermodal transport. This means the same container moves across different modes of transport is less than -0. 5 is greater than ship, truck, train, without unloading the goods inside. Fewer transfers mean fewer delays. Fewer delays mean lower cost. As adoption spread, shipping companies built vessels designed specifically for containers. These were called cellular container ships. Their holds contained vertical guide structures. Containers fit into these slots securely. Over time, ship sizes increased. Thousands of containers per voyage. Then tens of thousands. Larger ships created economies of scale. Fuel cost per container decreased as capacity increased. Crew sizes did not grow proportionally. Efficiency improved steadily. Containerization also changed port geography. Traditional city center docks became less suitable. Larger ships required deeper water. Larger cranes required more space. New container terminals were built outside dense urban cores, with rail and highway connections nearby. The system extended inland. Inland ports emerged. Rail corridors linked coasts to interior regions. Manufacturing adapted to this new reliability. Companies could source components globally. Assembly could take place far from raw materials. Supply chains lengthened, but coordination improved. Containerization supported what economists call globalization. Production distributed across countries. Consumption concentrated in large markets. The metal container became a quiet symbol of this integration is less than Hashone. Zero hash is greater than uniform. Stackable. Interchangeable. It does not reveal its contents. It simply moves. Refrigerated containers expanded possibilities further. These are called reefers. They maintain controlled temperatures. Perishable goods can now travel long distances. Meat, fruit, pharmaceuticals. Standardization also improved insurance and logistics planning. Cargo volumes became easier to measure. Routes became easier to schedule. Digital systems later enhanced this coordination. Tracking numbers, electronic documentation, real-time data exchange. Yet the core principle remained simple. Move the box. Do not move the contents. This simplicity hides complexity. Behind each container is a contract, a production plan, a delivery schedule. But physically, it is still a steel box. By the late 20th century, containerization dominated general cargo shipping. Break bulk declined sharply. Ports around the world adopted compatible standards. International trade agreements supported integration. The container became part of everyday infrastructure, so common that it often goes unnoticed. If you stand near a major port today, you will see stacks of containers in uniform rows. Different colors, different company names, same dimensions. Order replaces randomness. Predictability replaces delay. Containerization did not eliminate all challenges, is less than #0. 5 hash is greater than weather, still matters. Port congestion still occurs. but the baseline efficiency improved permanently. Global trade volumes expanded rapidly after widespread adoption. Shipping costs as a share of product value decreased. This allowed more goods to move profitably across oceans, even lower value items. The revolution was not loud. It was procedural, a redesign of how goods are handled. Steel boxes, standard measurements, coordinated infrastructure. Together, they reshaped global commerce. And they set the foundation for the massive vessels that now cross the oceans. In the next section, we will look closely at those vessels, their structure, their scale, and their daily operation. Now we move into the giant container ships of today. Modern container ships are built for scale. They are long. They are wide. They are deep. Some stretch longer than 3 football fields. Many rise high above the waterline when fully loaded. Their decks carry stacks of containers arranged in precise rows. Each container locks into place. Each stack follows a loading plan. The structure of these ships is deliberate. The hull is made of reinforced steel. It must withstand waves, wind, constant stress. Below the deck are cargo holds. Inside the holds are vertical guides called cell guides. Containers slide into these slots. They are stacked one above another is less than Hasson. 5 hash is greater than above deck. Containers are secured with twist locks and lashing rods. Stability is calculated carefully. Weight distribution matters. Heavy containers are placed low, lighter ones higher. The ship's balance depends on this arrangement. Engineers use computer software to design loading plans. These plans account for destination ports, weight limits, and structural stress. A modern, ultra-large container vessel can carry more than 20,000 TEUs. That means over 20,000 20-foot equivalent units. Each one sealed, each one tracked. Propulsion comes from large marine diesel engines. These engines are among the most powerful reciprocating engines in the world. They turn a single large propeller, often several meters in diameter. The ship moves steadily, at speeds typically between 15 and 24 knots. Speed is balanced with fuel efficiency. Fuel is a major operating cost. Many ships now use low-sulfur fuel oils to comply with international environmental regulations. Some are being designed to use alternative fuels such as liquefied natural gas. The bridge sits high above the deck, near the stern on many modern designs. From here, officers monitor navigation systems, radar, satellite positioning, automatic identification systems. The bridge is quiet. Screens glow softly. Alarms signal unusual conditions. The crew is smaller than many expect, is less than hazon. Zero hash is greater than. Often, fewer than 30 people manage the entire vessel. Automation reduces manual tasks. Crew members rotate watches. They monitor course, weather updates, engine performance. Engineers maintain machinery below deck. Routine inspections prevent failure. Life on board follows a schedule. Work shifts, meals, maintenance routines. Voyages can last several weeks, sometimes longer. Ships follow established trade routes across the Pacific, across the Atlantic, through the Indian Ocean. Major east-west routes connect manufacturing hubs in East Asia with consumer markets in North America and Europe. These routes are dense with traffic. For example, the Port of Shanghai handles tens of millions of TEUs each year. It is one of the busiest container ports in the world. Ships arriving there follow precise arrival windows. Berths are assigned. Pilots board to guide vessels into port. Tugboats assist in tight harbor spaces. Once docked, cranes begin unloading almost immediately. Turnaround time is critical. A ship generates revenue when it is moving cargo, not when it is waiting. Larger ships improve efficiency per container, but they also require deeper ports, stronger quay walls, taller cranes. Port infrastructure has expanded to accommodate this growth. Not every port can receive the largest vessels. Some routes rely on smaller feeder ships is less than #0. 5 is greater than. These distribute containers to regional ports. This creates a hub and spoke system. Large ships connect major hubs. Smaller ships connect secondary ports. Stability at sea is managed continuously. Ballast tanks adjust weight distribution. Water is pumped in or out as needed. Weather routing systems help avoid severe storms. Crews monitor forecasts. Despite their size, container ships are designed for flexibility. They can adjust speed to meet schedules. Slow steaming reduces fuel consumption when demand allows. The economics of these vessels depend on high utilization. Empty space reduces profitability. Shipping lines coordinate networks of vessels. Alliances share capacity on major routes. Containers are booked months in advance. Digital systems manage cargo flows. Each voyage is part of a larger rotation. A ship may stop at several ports before returning to its origin. Schedules are published. Customers plan inventory around expected arrival times. The scale can feel abstract, but it becomes clearer with examples. A single large ship might carry electronics, furniture, clothing, machinery, thousands of suppliers, thousands of buyers, all inside standardized boxes. Safety regulations govern these vessels. International conventions set standards for construction, equipment, crew training. Inspections occur regularly. Classification societies verify compliance is less than HAZON. 5 is greater than environmental rules limit sulfur emissions. Ballast water management reduces ecological impact. The system is technical, structured, regulated. And yet, from a distance, it appears simple. Rows of containers, moving slowly across open water. These ships are not isolated actors. They are nodes in a global network. Each voyage links factories to warehouses, warehouses to stores, stores to households. The giant container ship is a visible symbol of this connection. Steel carrying steel boxes. Built on decades of standardization, operated with careful planning. As we step back, we see patterns rather than individual vessels. Lines across oceans. Repeated routes. These routes form corridors of global trade. And to understand them fully, we now turn to the geography that shapes them. Now we move into the world's major shipping lanes. Shipping lanes are not random lines across water. They are shaped by geography, by economics, by history. When we look at a global map of vessel traffic, patterns appear. Dense corridors, repeated routes. Ships tend to follow the most efficient paths between major markets. Efficiency means shorter distance, safe passage, reliable infrastructure. One of the most important corridors stretches across the Pacific Ocean. This route connects East Asia with North America. Manufacturing centers in China, South Korea, and Japan ship goods eastward is less than HAZON. 0 is greater than major ports on the west coast of the United States. Receive them. The distance is vast. Thousands of nautical miles. Several weeks at sea. Yet the route is steady, repeated daily by multiple vessels. Another major corridor crosses the Atlantic Ocean. This route links Europe and North America. It has existed in various forms for centuries. Today, it carries containerized goods, vehicles, industrial equipment. The Atlantic route is shorter than the Pacific crossing, but still significant. A third major system spans from East Asia to Europe. Ships travel through Southeast Asia, across the Indian Ocean, toward the Middle East and the Mediterranean. This route depends heavily on a narrow artificial passage. The Suez Canal. It connects the Red Sea to the Mediterranean Sea. Without it, ships would need to sail around the southern tip of Africa, adding significant distance and time. The canal allows direct transit between Europe and much of Asia. It handles a substantial share of global trade. Transit through the canal is carefully scheduled. Ships travel in convoys. Speed is regulated. Narrow passages require precision. Geography concentrates traffic into choke points. A choke point is a narrow route where many ships must pass. Examples include straits and canals. Another major canal plays a similar role in the Western Hemisphere. The Panama Canal. It connects the Atlantic and Pacific Oceans, is less than has Hone. 0 hash is greater than. Before its construction, ships traveling between the east and west coasts of the Americas had to round Cape Horn. The canal uses a system of locks. Ships are raised and lowered between sea levels. This shortens travel time dramatically. It also shapes ship design. For many years, vessel size was limited by canal dimensions. The term Panamax described the maximum size that could pass. An expansion completed in the 21st century allowed larger ships to transit. These are sometimes called new Panamax vessels. Beyond canals, natural straits are equally important. The Strait of Malacca connects the Indian Ocean to the South China Sea. It is one of the busiest maritime passages in the world. The Strait of Hormuz channels energy exports from the Persian Gulf. Narrow waterways concentrate global movement. They create efficiency, but also vulnerability. When disruptions occur at choke points, delays ripple outward. Routes may be rerouted. Costs may increase. Open ocean lanes are less visible but equally structured. Ships follow great circle routes. These are the shortest paths between 2 points on a sphere. Navigation software calculates these arcs precisely, adjusting for weather and currents. Seasonal patterns influence routing. Monsoon winds affect Indian Ocean crossings. Winter storms shape North Atlantic voyages. Ice conditions influence Arctic navigation. Though Arctic routes remain limited and seasonal is less than has Hone, 5 hash is greater than. Shipping lanes also reflect economic geography. High traffic flows between regions with complementary trade relationships. Manufacturing exporters. Large consumer markets. Energy-producing regions. Industrial importers. Over decades, these patterns stabilize. Companies design service loops around them. A service loop is a repeating sequence of port calls. For example, a ship might depart East Asia, stop at several ports, cross the Pacific, call at multiple North American ports, then return. This loop may take weeks. Then it repeats. Multiple vessels operate on staggered schedules, ensuring frequent departures. Shipping lanes are supported by international maritime law. The United Nations Convention on the Law of the Sea defines territorial waters and navigation rights. It provides a framework for freedom of navigation in international waters. Most major trade occurs on the high seas, beyond national territorial limits. Coastal states manage port access, but ocean transit remains broadly open. Safety is coordinated through traffic separation schemes. In busy areas, ships follow designated inbound and outbound lanes, similar to highways at sea. This reduces collision risk. It improves predictability. Modern tracking systems allow authorities to monitor vessel positions continuously. Automatic identification systems broadcast ship data. On a digital map, the world's shipping lanes resemble illuminated threads is less than #0. 5# is greater than crossing oceans, converging at narrow passages. These threads connect continents. They form the physical network of global trade. Geography defines the framework. Economics fills it with movement. Without canals, routes would lengthen. Without straits, detours would multiply. Infrastructure reduces friction. It shortens time. Over centuries, shipping lanes have become more structured, more measured, more data-driven. Yet the principle remains constant. Ships move where trade demand directs them. The ocean is wide, but traffic concentrates along predictable paths. And at the ends of these paths lie ports, where sea meets land. In the next section, we will step into those ports to see how containers transfer from ship to shore. Now we move into ports, where the world touches land. A port is where sea meets land. It is a transfer point, a controlled boundary. Ships arrive from open water. Containers leave by road or rail. This transition is organized, timed, measured. As a container ship approaches harbor, a harbor pilot boards. The pilot knows local waters, depths, currents. Tugboats may assist. They guide the vessel gently toward the berth. The ship slows. Lines are secured. Engines reduce power. Once docked, port operations begin quickly. Time at berth is valuable. Schedules are tight is less than hazon. 5# is greater than towering. Gantry cranes line the quay. They move on rails, extending over the ship's deck. Each crane operator follows a loading plan. Containers are lifted vertically, then lowered onto waiting vehicles. The motion is repetitive, precise, coordinated. A single crane can move many containers per hour. Multiple cranes may work on one vessel at once. The goal is efficiency. Reduce idle time. Containers are placed onto terminal trucks or automated guided vehicles. These vehicles carry them to stacking yards. In the yard, containers are organized in rows, sorted by destination, sorted by pickup schedule. Specialized stacking cranes lift and reposition them. Space is used carefully. Ports handle large volumes daily. For example, the Port of Singapore is one of the world's busiest transshipment hubs. Many containers there are not final deliveries. They transfer from one ship to another. Transshipment connects regional routes to long-distance routes. It strengthens the network. In the United States, the Port of Los Angeles handles large volumes of cargo from across the Pacific. Containers arriving there move inland by rail and truck. Ports vary in size. Some handle millions of TEUs per year. Others focus on regional trade. Yet the core process is similar. Arrival, unloading, sorting, transfer. Customs procedures take place alongside physical movement is less than #0. 5# is greater than. Documentation is reviewed. Duties may be assessed. Many documents are now digital. Electronic data interchange systems transmit cargo information before arrival. This allows clearance processes to begin early, reducing delays. Security is also structured. Containers may be scanned. Random inspections occur. International regulations aim to protect trade while maintaining flow. Rail terminals often sit adjacent to container yards. Double-stack trains carry containers inland. Truck gates manage outbound traffic. Drivers follow scheduled pickup times. Congestion can occur when volume exceeds capacity. Ports respond by expanding infrastructure, adding automation. Some modern terminals use automated stacking cranes, guided by software, monitored remotely. Automation improves consistency. It reduces manual handling. Yet human coordination remains essential. Operators supervise systems. Technicians maintain equipment. Ports are economic centers. They generate employment, support logistics companies. Warehouses cluster nearby. Distribution centers expand along transport corridors. The physical layout of a port reflects scale. Deep water berths for large vessels. Wide turning basins. Dredging maintains sufficient depth. Navigation channels are marked clearly. Environmental management is increasingly important. Shore power systems allow ships to shut down engines while docked is less than #0. 5# is greater than reducing emissions. Noise and traffic are monitored. Ports exist within communities. Efficiency depends on coordination between many actors. Shipping lines, terminal operators, customs agencies, trucking companies. Each has a defined role. Each relies on timing. A delayed vessel affects yard space. Yard congestion affects truck queues. The system is interconnected. Small disruptions can ripple outward. Yet most days follow routine patterns. Ships berth, cranes lift, trucks depart. Containers move inland to warehouses. There they are unpacked. Goods are sorted again. Some items travel directly to stores. Others move to regional distribution hubs. Ports are not endpoints. They are transitions. They translate ocean transport into land transport. Without ports, shipping lanes would have no connection to daily life. From above, a large port appears geometric. Grids of containers, parallel cranes. Order replaces randomness. Sequence replaces chaos. This structured environment supports global trade at scale. Millions of containers per year. And behind each container is a specific story, a product, a destination. In the next section, we will follow one of those containers closely, from factory floor to final delivery. Now we move into the journey of an everyday object. Global shipping does not operate in isolation, is less than has hone. Zero hash is greater than. It is shaped by rules, agreements, standards. These frameworks create predictability. Predictability supports trade. At sea, safety and environmental rules are largely coordinated through the International Maritime Organization, often called the IMO. It is a specialized agency of the United Nations. Member states adopt conventions. Conventions set minimum standards. One major convention is SOLAS, the Safety of Life at Sea Convention. It defines requirements for ship construction, equipment, emergency procedures. Another is MARPOL, the International Convention for the Prevention of Pollution from Ships. It limits oil discharge, controls waste disposal, regulates air emissions. These agreements are technical, detailed, structured. They create a shared baseline across nations. Ships sail between jurisdictions, from one country's port to another's. Each vessel is registered under a flag state. The flag state enforces international rules. Port states also inspect visiting ships. This is called port state control. Inspectors verify certificates, safety systems, crew qualifications. If deficiencies are found, corrective action is required. Trade rules extend beyond the ship itself. Goods crossing borders are subject to customs law. Tariffs may apply. Quotas may apply. Many trade relationships are structured through agreements negotiated under the World Trade Organization is less than #0. 5 is greater than the WTO, provides a framework for dispute resolution. It promotes transparency in trade policy. Regional agreements also shape shipping flows. Free trade areas reduce or eliminate tariffs between members. When tariffs change, shipping patterns adjust. Routes shift gradually. Governance is not only international. National maritime authorities regulate domestic ports. They oversee harbor safety, infrastructure standards, environmental compliance. Ports operate under concession agreements. Terminal operators lease space, invest in equipment. Legal clarity reduces uncertainty. Uncertainty increases cost. Insurance markets also rely on rules. Marine insurers assess vessel condition, route risk, cargo type. Classification societies inspect ships. They verify structural integrity, machinery standards. A vessel without proper classification cannot easily obtain insurance. Environmental governance has grown more detailed over time. Emission control areas limit sulfur content in fuel. In 2020, the IMO implemented a global sulfur cap, reducing allowable sulfur in marine fuel to 0.5%. Ships adapted by using low sulfur fuel or installing exhaust gas cleaning systems. Ballast water management is another regulated area. Ships take on ballast water for stability. That water can carry marine organisms. International rules require treatment systems. To reduce ecological impact is less than Hashone. 5 is greater than governance, also addresses labor conditions. The Maritime Labor Convention sets standards for crew welfare. It defines working hours, living conditions, medical care. Shipping depends on skilled seafarers. Standards protect both workers and operations. Security frameworks developed in response to global risks. The ISPS code sets ship and port security requirements. Access control, identification systems, security plans. These measures aim to reduce threats without halting trade. Governance creates layers: international, regional, national. Each layer interacts with the others. Enforcement depends on cooperation, data sharing, inspection regimes. Disputes sometimes arise over tariffs, over environmental compliance. Resolution mechanisms aim to prevent escalation. Beyond formal law, industry associations influence standards. Best practice guidelines circulate among carriers. Voluntary initiatives encourage emissions reduction, digital transparency. Governance evolves gradually. In response to accidents, environmental events, economic shifts. After major maritime incidents, safety rules are often reviewed. Policy changes tend to be technical, specific, data-driven. Shipping companies adapt through compliance departments, legal teams, operational adjustments. Compliance has cost, but it also reduces risk, is less than Hasson. 5 hash is greater than. Stable governance lowers insurance premiums, encourages investment. Investors seek predictable regulatory environments. Digitalization is now part of governance. Electronic bills of lading are being tested and adopted in some corridors. Data standards improve interoperability. Customs declarations move electronically. Transparency reduces fraud, speeds clearance. Climate policy is increasingly central. Discussions include carbon intensity targets, alternative fuels. Some regions implement emissions trading systems that include maritime transport. This creates economic signals, encouraging efficiency. Governance does not eliminate volatility. Markets still fluctuate, but it provides structure, a shared rulebook. Without that rulebook, coordination across oceans would be fragile. With it, ships from many nations can dock in foreign ports, exchange goods, continue onward. The system is imperfect, yet it functions daily. Governance is quiet, often unnoticed, but it underpins the visible flow of containers. In the next section, we will examine the vulnerabilities within this system and how disruptions ripple across the network. Now we move into risks and resilience in global shipping. Global shipping is steady, but it is not immune to disruption. The system is efficient. It is also tightly interconnected. When one link slows, others feel the effect is less than Hasson. 5 hash is greater than. Risk exists at many levels: natural, technical, economic, political. Weather is a constant factor. Storms alter routes. High waves reduce speed. Modern forecasting allows ships to plan around severe systems, but delays still occur. Seasonal patterns matter. Monsoon cycles, hurricane seasons. Ports may suspend operations temporarily for safety. Geography can create choke points. Narrow passages concentrate traffic. The Suez Canal is one such passage. It connects the Mediterranean Sea to the Red Sea. A blockage there can delay hundreds of vessels. Ships may reroute around Africa, adding time and fuel cost. The Panama Canal is another strategic corridor. It links the Atlantic and Pacific Oceans. Capacity limits or drought conditions can restrict transits. These canals shorten global routes. When constrained, trade patterns adjust. Mechanical failure is another risk. Ships are complex systems: engines, navigation equipment, Power generation. Regular maintenance reduces breakdowns. Classification inspections verify seaworthiness. Still, unexpected faults can occur. Repairs may require port diversion. Port congestion can create systemic strain. When import volumes surge, terminals fill. Yard space becomes limited. Trucks wait longer. Ships anchor offshore. Congestion increases turnaround time, which affects vessel schedules globally, is less than has honed. 5 is greater than supply chains, often operate on just-in-time principles. Minimal inventory. Frequent replenishment. This reduces storage cost, but increases sensitivity to delay. Labor disruptions can slow movement. Port strikes. Driver shortages. Even short interruptions can create backlogs. Geopolitical tensions influence routing decisions. Sanctions may restrict trade with certain states. Shipping lines adjust services to remain compliant. Insurance premiums may rise in high-risk areas. Piracy has affected some regions historically. International naval patrols and onboard security measures have reduced incidents in many areas. Cybersecurity has become increasingly relevant. Ports rely on digital systems, terminal operating software, electronic documentation. A cyber attack can disrupt cargo visibility or gate operations. Companies invest in network security, data redundancy. Economic volatility also shapes resilience. Freight rates fluctuate with demand. Overcapacity can depress rates. Surges can elevate them. Shipping lines manage capacity through alliances, adjusting sailing frequency. Alliances allow carriers to share vessels on major routes, spreading risk. The global pandemic in 2020 demonstrated systemic fragility. Factory shutdowns reduced output. Then consumer demand shifted rapidly. Container imbalances developed. Some regions faced equipment shortages is less than has honed. 5 is greater than recovery required time. Repositioning containers. Expanding port capacity. Resilience involves diversification. Multiple suppliers. Multiple routes. Some companies increase safety stock levels, accepting higher inventory cost for stability. Governments assess strategic dependencies, especially for medical goods. Energy supplies. Infrastructure investment strengthens long-term resilience. Deepening channels. Expanding terminals. Digital tracking improves transparency, allowing earlier response to delay. Predictive analytics can forecast congestion trends. Weather routing software optimizes fuel and safety. Environmental change introduces additional uncertainty. Rising sea levels affect port design. Extreme weather frequency may increase in some regions. Adaptation plans include elevated infrastructure, reinforced breakwaters. Insurance mechanisms distribute financial risk. Marine insurance pools losses across fleets. Reinsurance spreads exposure globally. Financial instruments hedge fuel price volatility. Despite vulnerabilities, global shipping has historically demonstrated adaptability. Routes shift. Technology advances. Redundancy is built gradually. Lessons are integrated into regulation. The system is dynamic, not static. It absorbs shocks, then recalibrates. Most disruptions are temporary, though their impacts can be significant, is less than Hashon. 5 hash is greater than resilience depends on cooperation between ports, carriers, regulators. It depends on information flow and coordinated response. When one corridor narrows, alternatives expand. When demand changes, capacity adjusts. Global shipping remains a backbone of trade, even during strain. Understanding its risks clarifies its importance and its complexity. In the next section, we will look forward to emerging technologies and the future direction of maritime transport. Now we move into the future of global shipping. The future of global shipping will likely be evolutionary, not sudden. The system changes step by step through regulation, through technology, through market pressure. One central theme is decarbonization. Shipping currently relies largely on heavy fuel oil and marine diesel. These fuels emit carbon dioxide when burned. The International Maritime Organization has adopted greenhouse gas reduction targets, aiming to reduce total emissions over the coming decades. Achieving this requires multiple approaches: fuel innovation, efficiency gains, operational change. Alternative fuels are under active development. Liquefied natural gas has been adopted on some vessels. It reduces sulfur emissions and lowers carbon dioxide compared to heavy fuel oil. Yet it is not carbon-free. Methanol is being tested as a marine fuel. It can be produced from renewable sources, is less than Hashon. 5 hash is greater than ammonia, is also being studied. It contains no carbon, but presents storage and safety challenges. Hydrogen is another possibility. Though energy density and infrastructure remain constraints, fuel transition requires new engine designs, new bunkering facilities. Ports will need updated storage systems, safety protocols. Change will therefore be gradual. Efficiency improvements continue alongside fuel innovation. Hull designs are optimized to reduce drag. Propellers are refined. Air lubrication systems reduce friction between hull and water. Slow steaming has already reduced fuel consumption in many trade lanes by operating vessels at slightly lower speeds. Digital optimization is expanding. Ships collect operational data, fuel use, engine performance. Analytics platforms recommend efficient routing, weather-adjusted speed profiles. Autonomous technologies are being tested. Some short-route vessels operate with high degrees of automation. Fully autonomous ocean-going container ships remain experimental. Regulatory and safety frameworks must adapt before widespread deployment. Automation is more advanced inside ports. Automated stacking cranes, driverless yard vehicles. These systems improve consistency and reduce human exposure to certain hazards. Digital documentation is another area of change. Electronic bills of lading reduce paperwork. Speed up transfer of ownership is less than hash-own. 5-hash is greater than blockchain-based systems have been piloted, though industry-wide adoption varies. Standardization is essential. Without shared data standards, digital systems cannot fully integrate. Supply chain visibility is expanding. Shippers can track containers in near real time, monitor estimated arrival times. This transparency allows better inventory planning. Infrastructure investment will shape the future. Larger vessels require deeper berths, stronger cranes. Some ports expand to handle ultra-large container ships. At the same time, regional ports may specialize, focusing on feeder services. Geopolitical trends may influence network structure. Some countries promote nearshoring, locating manufacturing closer to consumer markets. This could shorten certain supply chains, while long-distance trade remains significant. Climate change may alter Arctic sea routes seasonally. Reduced ice coverage has opened limited navigation windows in some years. However, infrastructure and environmental concerns remain substantial constraints. Financial markets also guide transition. Investors increasingly assess environmental performance. Access to capital may depend on sustainability metrics. Carbon pricing mechanisms may expand, influencing fuel choice. Education and workforce development will evolve. Seafarers will need training on alternative fuel systems, digital tools. Port technicians will manage automated systems is less than hash-own. 5-hash is greater than. Despite innovation, core principles will remain. Ships will carry standardized containers. Ports will transfer them to land networks. Trade will depend on reliability, predictability. The scale of maritime trade is unlikely to disappear. It underpins global economic integration. Change will likely balance efficiency with sustainability, technology with regulation. Progress will be measured in incremental gains, fleet renewal cycles, infrastructure upgrades. Some ships sailing today will operate for decades. New vessels will gradually replace older designs. The future of global shipping is therefore layered. Old systems adapting, new systems emerging. It is not a single transformation, but a continuous process. In the final section, we will step back and reflect on how this quiet system shapes daily life across continents. Now we move into the quiet network beneath everyday life. Global shipping is rarely visible in daily life, yet it is present in quiet ways. It shapes what is available, when it is available, at what cost. A store shelf appears simple, rows of products. Behind each product is distance, coordination, timing. A smartphone may contain components manufactured in several countries. Processors, displays, batteries. Those components travel by sea between production stages. Clothing often follows a similar path, is less than #0. 5 is greater than cotton, grown in one region. Fabric woven in another. Garments assembled elsewhere. Containers carry these intermediate goods quietly across oceans. Food systems also rely on maritime transport. Grains, coffee, refrigerated fruit. Specialized refrigerated containers maintain temperature, protecting perishable cargo. Energy supply chains depend on shipping as well. Crude oil, refined fuels, liquefied natural gas. Large tankers move these resources between producing and consuming regions. Industrial production relies on bulk materials, iron ore, coal, bauxite. Bulk carriers transport these raw inputs at scale. Even construction materials may arrive by sea. Cement, steel products. The network is broad, diverse. Shipping influences prices indirectly. Freight costs are one component of total product cost. When freight rates rise sharply, import prices can adjust. When routes operate smoothly, costs stabilize. The presence of reliable shipping expands consumer choice. Products from distant climates become accessible year-round. Manufacturing can specialize geographically. This specialization increases efficiency. It also increases interdependence. Interdependence means that disruptions travel across borders. A factory pause in one region can affect inventories elsewhere. Yet most of the time, the system operates quietly. Ships depart is less than #0. 5 is greater than arrive. Depart again. Ports transfer containers methodically. Rail lines extend inland. Warehouses receive shipments. Retailers restock shelves. This rhythm is steady, repetitive. Maritime trade also supports economic development. Coastal cities often grow around ports. Employment clusters in logistics and related services. Export industries depend on reliable outbound routes. Agricultural producers. Manufacturers. Shipping connects them to global markets. The network does not eliminate inequality, nor does it guarantee stability. But it provides infrastructure for exchange, a framework for cooperation. International standards allow vessels from many nations to share sea lanes, to dock at foreign ports. This routine cooperation is practical, technical. It is rarely dramatic. Environmental considerations are now part of everyday logistics decisions. Companies measure carbon footprints. Consumers ask about sourcing. Shipping lines respond with efficiency programs, alternative fuel trials. The quiet system adjusts gradually, not through headlines alone, but through incremental design changes. The ocean itself remains constant, vast, open. Trade routes trace consistent corridors across it, following geography and economics. Satellites track vessel positions. Navigation systems maintain safe distance. Crew members stand watch in shifts is less than #0. 5 is greater than monitoring instruments. On land, planners analyze data, forecast demand. The scale can feel abstract. Millions of containers per year. Yet its effects are tangible. A package arriving on time. A stocked supermarket. Shipping rarely calls attention to itself. It is designed not to interrupt, but to support continuity. This continuity shapes modern expectations of availability, of connection. Global shipping is therefore both distant and immediate, operating far offshore, influencing daily routines. It links climates, economies, communities, not through spectacle, but through repetition. Container by container, voyage by voyage. When viewed as a whole, it forms a quiet network. Structured, regulated, adaptive. It is one of the foundations of contemporary global life. As we conclude, we return to the simple image of a container moving across calm water. Steady, measured. That steady movement continues beyond this explanation, connecting shores long after the narration ends. Global shipping continues whether we notice it or not. Containers move across open water. Ports transfer them with quiet precision. Trains and trucks carry them inland. This system is structured, measured, repeated each day. It connects climates, industries, households, not through spectacle, but through consistency. The shelves we pass, the devices we use, the materials that build our cities, all move through this network at some point. Most voyages are uneventful. Most transfers routine. And that reliability is the point. A quiet system, operating at global scale. As you step away from this explanation, the ships are still moving. Steady, coordinated, connecting the world in ways both distant and immediate.